Hello students, welcome back to the one more session of microcontroller and embedded systems. This is Vasanth Nayak from Canara Engineering College. In this session, we are going to study or we are going to understand like how computational models are defined in embedded system. Like how computations are defined, what kind of models are used in to define the computation in embedded system, what are the different types of computational models. All these we'll going to study in this session. So there are different computational models used or defined in embedded system design. First one is called as data flow graph or data flow diagram, DFG model. Second one is control flow graph or control flow diagram, CDFG model. Third one is state machine model. Here we will study finite state machines. And fourth one is a sequential programmer method or model. Fifth one is concurrent communicating process model. And the last one is object oriented model. So in this session we will study all these different types of model, how the computations are defined in each model we will discuss in this session. Here first we will see data flow graph model, or you can call this as data flow diagram. So data flow model, actually this data flow model or data flow graph model translates the data processing requirement into data flow graph. It actually tells about how the data is processed inside the system. Okay, data flow graph model is a data driven model in which program execution is determined by the data. So here certain notations are used to write the data flow graph. The notations are like a process are represented by the circle, and the arrow is used to represent the flow of information from the input to the output. For example, any circle having input arrow or inward arrow indicates the process or circle is receiving the data, and if the process or circle is having outward arrow, then it indicates it is transmitting the data to the either to the another process or output. So this type of models are used when there is a very high computational intensive task has to be performed. In that case, DFG model is used. Suppose, like I have an example here to the how computation happens, and this example is for a DFG model. Like the I have a computational requirement like x is equal to a plus b and y is equal to x minus c. So how it is represented in a DFG model? As we know, in DFG model we represent the process by circle. Here we have input a, b and c. So the process is represented by circle. This process indicates that it is addition process is going on, and this process indicates here its subtraction process is going on. So this process receives the input a and b, and it will compute the value, that is the output x, that is given to one more process. And here in this process subtraction is going to happen, and this process will take input from input from other source. So finally the output it gives is y. So this is in this way the computational happens in a DFG model. So DFG model is said to be a acyclic DFG or ADFG because it doesn't contain multiple values for the input variable. For example, here the variable a, this particular input has got different value like a comma b comma c, like a comma b comma c, like multiple values. Then it is called as non-acyclic. Otherwise, it is called as acyclic DFG model. So this is about DFG model. So next we will see about control data flow graph flow graph or control data flow diagram 3D-FG model. So the second model is a control data flow graph or diagram, control data flow diagram model. It is also called as 3D-FG model. This is equivalent to nothing but data flow chart. And the only difference between this model and the other model, that is the data flow graph model, is this model is not only data driven, it is also controlled by conditional constructs. Here the execution is controlled by data, and it doesn't involve any control operations in case of data flow model. But in case of control DFG model, it is controlled by conditional constructs. Conditional constructs, as we know, like for loop, while loop, all these are the conditional constructs. So 3D-FG uses both data flow as element and conditional construct as decision makers. So conditional constructs, they are used here as decision makers. 3D-FG contains both data flow and decision nodes, whereas DFG contains only data flow nodes. That we understood. Now we will see we'll see one example here. If flag is equal to 1, then I want to execute this process, x is equal to a plus b, else y is equal to a minus b. This requirement contains a decision making process. In the decision making process, decision making process in the sense like flag is equal to 1. So this requires a 3D-FG model. This cannot be modeled by using data flow graph. So it should be modeled by using 3D-FG. So you can see here, in such type of situation, the control node is represented by data diamond block, which is the decision making element which we normally use in flowchart. So here we represent the conditional or constructs by means of diamond block. In this we'll mention like flag is equal to, if the flag is equal to 1, then it will go to this process of addition, where it will take the input a and b. If it is not equal to 1, then it will go to the other process. It will go to the other data flow node, where it will take input a and b, and it will do this process like subtraction. So in this way, the 3D-FG translates the requirement which is modeled to a concurrent process model. The decision on which process is to be executed is determined by the control node. So here the decision which process has to be executed is determined by the control node. So next we will see state machine model. So we studied, first one is a data flow model, second one is a control data flow model. The data flow model is driven by the data, and control data flow model is driven by the conditional constructs or control. Third is the state machine model. It is used for modeling a reactive or event-driven embedded system whose processing behavior is dependent on the transition. Embedded system used in the control and industrial applications makes use of such type of model. Like this model is used for such type of embedded system, which makes transition of the state. It moves from one state to other state. So the state machine model describes the system behavior with the state, event, action and transition. So this model describes a system behavior with the states, events, action, transition. What is a state? It is a representation of the current situation or current variable, something like that. Event is an input to the state. That event acts as a stimulation for state transition. Transition is the movement from one state to another state. Action is an activity to be performed by the state machine. So now, so this is well explained by the finite state machine FSM model. So any system which is having a finite number of states can be modeled by finite state model. So let us consider an example of a design of an embedded system for driver passenger seat belt warning, and we will try to model this by using a finite state machine model. So the requirements are something like this: like when the vehicle ignition is turned on and the seat belt is not fastened by the passenger within the 10 seconds of the ignition on, the system generates the alarm signal for 5 seconds. The alarm is turned off when the alarm time expires, or if the driver passenger fasten the belt, or if the ignition is switched off, whichever happens first. So here the states are alarm off, waiting, and alarm on. Like it will move from alarm off to waiting to alarm on, or alarm on to waiting to alarm off. And the events which makes this state transitions are ignition key on, ignition key off, timer expire, alarm timer expire, and seat belt on. These are the events responsible for these state changes. So how we can model this by using FSM? So here you can see in the FSM we have states are represented by like alarm off, waiting, and alarm on. Alarm off, waiting, and alarm on. All these are different states. And events are like ignition key on, ignition key off, seat belt on, timer expire, alarm timer expire, etc. Initially, when the driver switch on the ignition key for the 10 seconds, for the like ignition key on event triggers the 10-second timer and transitions the state to waiting. So when you switch on the driver or driver, when you say switch on the ignition key, that is here actually ignition key is the event that will make the state transition from alarm off to waiting. So this is like it will give 10 seconds for 10 seconds for the driver and passenger to fasten the seat belt. If the seat belt is on, by the time the driver or passenger fasten the seat belt is on, then it will move from this state to alarm off state. From waiting state to alarm off state, or in between, if the driver switch off the ignition key, then it will move from wait state to alarm off state. Otherwise, it will move from wait state to alarm on state. Here, timer starts and timer will run. Timer will imitate different like audio tone for 5 seconds. And if the And when the wait timer expires in the waiting state, the event timer expire is generated and it transitions the state to alarm on from the waiting state. So here when the timer expires, it will move from alarm on to alarm off state. So when the timer expires, then it will move from alarm on to alarm off. Or by the time, or when the seat belt, if the passenger or driver fasten the seat belt, then that time also it will move from timer off to it will off the timer and it will move from alarm on to alarm off state. Or if the driver switch off the ignition, then it will move from alarm on to alarm off state. So here we have one more FSM that will gives the picture of a waiting state. I told in the previous diagram we have 3 states like totally alarm off, waiting, and alarm on. Now this waiting state is totally represented by one more FSM, that is The wait state is implemented by using a timer. The timer also has a certain set of states and events for the state transition, like idle, ready and running. These are the state, and the event is when the timer is for like load timer event is executed, then the timer is loaded with the new count and it will move from idle state to ready state. When the start timer event is executed, then it will move to running state, and here now the LRAM will run LRAM will run and it will decrement when it totally when it decrements to 0, that time event stop timer or timer expires and it will move to the idle state. So the explanation of this one is given here. As seen from the FSM, the timer state can be either idle, ready or running. During the normal condition, when the timer is not running, it is said to be in the idle state. If the timer is said to be in the ready state, if timer is said to be in the ready state when the timer is loaded with the count corresponding to the required time delay. Timer remains in the ready state until a start timer event occurs. The timer changes its state to running from the ready state on receiving the start timer event and remains in the running until the timer count expires or a stop timer event occurs. The timer state changes to idle from the running on receiving the stop timer or timer expire event. So next we will see the FSM for tea, coffee vending machine. Now we will see another example here. Design an automatic tea, coffee vending machine based on the FSM model. So in the diagram you can see here, the tea coffee vending machine is initiated by user inserting 5 rupees coin. So these are the status like state A, state B, state C, state D, and here it is shown like state A is nothing but wait for the coin. So here the machine waits for the coin from the user. When the user inserts the coin, then event takes place is insert coin. Then this will move this from this state to state B. So in the state B, it waits for the user to input whether user wants tea or coffee. When the corresponding event is here, user press the T button, then it will move from this state to state C, where it will dispense the tea to the user, and action is done, it will return to the original state. Well, otherwise the user press the coffee button press, the event is coffee button press, then it moves from state B to state D, where it will dispense the coffee and action is done. Otherwise, if the user press cancel button, the coin will return the coin. That is, the event is cancel button and action is coin out, and it will wait for the user to insert the coin. So this is the FSM model for tea coffee vending. Now, so here it is the explanation for this one. In the FSM representation contains 4 states, namely wait for coin, wait for user input, dispense tea, dispense coffee. These are the 4 states. The event insert coin makes the transitions of the state to wait for user input. The system stays in this state until user input is received from the button cancel tea coffee. If the event is triggered in a wait state is cancel button press, then the coin is pushed out this and the state transition to wait for coin. If the event received in the wait state is either tea button press or coffee button press, the state changes to dispense tea or dispense coffee respectively. So now we will see the one more example, that is public telephone unit based like design a coin operated public telephone unit based on the FSM model. So we'll take another example like coin operated public telephone unit, and let us try to model it by using FSM. So here the calling process is initiated by lifting the receiver off hook of the telephone unit. After lifting the phone, the user needs to insert the coin. If the line is busy, the coin is returned on placing the receiver back on the hook. If the line is through, if the user is allowed to talk till 60 seconds, and at the end of the 45th second, it prompts for inserting another coin for continuing the call. If the user doesn't insert another 1 rupee coin, the call is terminated on completing the 60 seconds time slot. So now we will see the FSM model for this one. Here you can see these are the different states: state A, state B, state C, state D, state E, state F. And other than that, we have like this is the starting state. Other than this is the out of order state. We will see this one. So actually initially it is the starting state. On lifting the receiver, like when the user lifts the hook, lift the receiver, then it will move from state A to state B, that is lift the receiver, and it will wait for the user to insert the coin. The corresponding event is the coin insert. If the action is okay, then it will move into state C, and it will wait for the user to enter the valid number. The event is valid number, and it will move to state D. And if the line is available, then it moves to the state E and action for, and it will act, and it will like monitor the duration. If the event is timeout, like at the end of 45th second, like at 45th second, then it will prompt to insert the coin. If the coin is inserted, then it will continue the call. Otherwise, it will disconnect the call, and event is place the receiver on the hook, and action is done. In between, there are two other states. That is, at this stage, if the user enters invalid number, then event is invalid number, action is display error. Then it will move to the state H, where it will move to the return the coin, and it will move to the original state. So at the state D, if the line is busy, then action is display error. Then the event is like line fault, line busy, and it will move to the state G. And here it will return the coin, and it will move to the state A. Otherwise, it will remain the state A. And state 1 is like the out of order state, where the telephone is not working. At that time, telephone is not working, or some problem with the machine. That time it will remain in the state 1. So this is the example for coin operated public telephone. Now, so most of the time, like FSM models are used for sequential, sequence driven program. So it cannot be used for concurrent driven processing method or concurrent driven program. So this limitation is addressed by one more FSM model, that is called as hierarchical or concurrent finite state model. It is the extension of the FSM for supporting concurrency and hierarchy. Now, HCFSM extends the conventional state diagram by the AND or decomposition of state together with the inter-level transition and broadcast mechanism for communicating between concurrent process. So, Student, so far we have covered different types of model. Then next we will move to the sequential or sequential program model. Students, now we will see sequential program model. Actually, sequential program model, in the sequential program model, everything proceeds in the sequential form, not concurrent form. So FSM are good choice for sequential programming model, but another important tool which is used for sequential programming model is flowcharts. Because the FSM approach represents the state, events, transitions and actions, whereas the flowchart, we know what is the use of flowchart. We have studied the flowchart in C programming. Flowchart models the execution flows. The flowchart models how the executions will take place. This will be shown by the flowchart. So execution function in a sequential program model. For this, let us see now the seat belt warning program this one execution function by using sequential programming model. So here there is the flowchart and here there is the program. So here it is like we have defined the macro. 1 is equal to 1. We have defined another macro, off is equal to 0. Then we have defined another macro, s is equal to 1, and we have defined another macro, no is equal to 0. Then we have function here, seat belt 1. Inside the function we have one more this one function, wait for 10 seconds. So initially when the user start the ignition, or the driver starts the ignition, then it will give 10 seconds for the user to fasten the belt, and it will check now. After 10 seconds it will check if the check ignition key is equal to on, and if the seat belt is equal to off. Then after 5 seconds it will set the timer. So after 5 seconds it will set the timer, it will start the alarm. It will set the timer for 5 seconds, it will wait for another 5 seconds to set the timer, and then it will start the alarm. So during that it will check whether the seat belt is whether still the user has not fastened the seat belt, or ignition key is off, or timer expired. Based on any of this condition, it will stop the alarm. So any one of the condition, it will stop the alarm. And here you can see like the flow chart, initially ignition key is on, then wait for 10 seconds, then ignition on, then based on the condition the flow chart proceeds. So now next we will proceed to the one more model, that is called as a concurrent or communicating process model. The concurrent or communicating process model concurrently executes the task process. So it is easier to implement certain requirements in concurrent processing model than the conventional sequential model. In the sequential model, everything has to be executed sequentially. So it is easier to implement certain requirements in the concurrent processing model. Now we will see the one more, this one, concurrent communicating process model. Concurrent communicating process model models the concurrently executing task process. It is easier to implement certain requirements in concurrent processing model than the conventional sequential executions. You know, in the sequential execution, everything has to be executed sequentially. So it is easier to implement certain tasks in the concurrent processing model, certain requirements in the concurrent processing model. Because the sequential execution leads to poor processor utilization, because when the task involves IO waiting, sleeping for specified duration, etc., then processors are not utilized properly, so it leads to poor processor utilization. So in the sequential execution of task, it leads to poor processor utilization. So how you overcome this one? This is overcome by means of dividing the task into multiple subtasks. It is possible to tackle the CPU usage effectively. But this process also has got certain disadvantages. What are the disadvantages? The disadvantages in the sense when you divide the task into multiple subtasks, then synchronization between that multiple subtask is a additional overhead. Like concurrent processing model requires additional overheads in task scheduling, task synchronization, and communication. So let us now see. Let us now take the same seat belt warning system, and now we will see how to model this in concurrent processing model. So in concurrent processing model, the seat belt warning system is split into 5 tasks. That is timer task for waiting 10 seconds, task for checking the ignition key, that is wait timer task, ignition key status monitoring task, seat belt status monitoring task, alarm control task, alarm timer task. So we have here 5 tasks and we cannot execute them randomly or sequentially. We need to synchronize their execution through some other mechanism, that is a concurrent mechanism. So here you can see for these above said examples, different types of events, like when you implement that in a concurrent model, different types of events are created. All those events are wait timer, expire, ignition on, ignition off, seat belt on, seat belt off, alarm timer start, alarm timer expire. Other than that, the task is like already I told you, I told you people, like wait timer, then ignition key status monitor, seat belt status monitor, then alarm control, alarm timer. There are like 5 tasks, five tasks are there. So now here you can see we have 5 tasks. This is one task, this is one task, this is one task, this is one task, this is one task. So let me start from this one, like the this one. So ignition seat belt status monitor task. Like when the seat belt is on, then it will trigger this event. It will trigger this event, like ignition off or seat belt on, something like that. So when the set event like when the set event seat belt off, like see when the event seat belt off, then it will trigger this task, like if ignition on and the seat belt is off, that means the ignition is on and the passenger has not fastened the seat belt, then it will start the alarm, and other things. From here it will trigger the other task, like this type of task. So here all the tasks are not sequentially executed or randomly executed, it is concurrently executed. So this is the example for concurrent executions. Now next we will move to the object oriented model. So an object oriented model is an object based model for modeling the system requirement. It disseminates a complex software requirement to simple well defined features called object. So what is the use of this one is object oriented model brings reusability, maintainability and productivity in the system design. So in object modeling, the object is an entity used for representing or modeling a particular piece of the system. Each object is characterized by a set of unique behavior and state. So class is an instant of an object. Class is an abstract description or a set of object, and it can be considered as a blueprint of an object. So here we know class represents the state of the object through member variables and object behavior through member functions. So these members are belongs to this class, like class represents the state of an object through member variables and member behavior through member functions. Like private member variables and functions are accessible only within the class, whereas public variables and functions are accessible within the class as well as outside the class. So this is related to this is the concept related to object oriented model. So with this student, we have completed another chapter. So next we will move to embedded firmware design and development. Thank you for your cooperation. Thank you.